Hello and welcome to your first virtual lesson of the 2020-2021 school year. Lots of 20s in there. I think I said enough. I'm just warning you that my dogs are out right now, so if you hear some barking because there might be a delivery or something going on, I apologize. I have put together notes for you that I've also posted on Schoology for you, so you can check those out. So they have all the examples and the notes. I do not expect you to write all of this down. Okay, so I repeat, I do not expect you to write all of this down. What I do expect is that you write down any important formulas that you think you might forget or want handy, and also the examples. All right, so let's get started. So today we're talking about the natural log function, both differentiation, which is section 5.1, and then section 5.2 covers integration. I think you've covered some of this before last year. I'm not quite sure to what depth. So when you come to class next and have questions, I'm happy to go over anything and we can all make sure we're on the same page. All right, so the definition of the natural log function now is going to be using an integral. So the natural log of x is the integral from 1 to x of 1 over t dt with a domain of all positive real numbers. So now if we look at this and we say, okay, what about this x? What if x is greater than 1? So if x is greater than 1, then my integral goes from 1 to something bigger than it, above the x-axis, therefore my natural log will be positive. And if x is less than 1, so I'm going from 1 backwards, okay, so then I'm going to get a negative integral value. So then the natural log will be less than 0 or negative. So that's kind of a good little visual to help remind you of when your natural log values will be positive and when they will be negative. Some additional properties of natural log function is that the domain is all real numbers and that all real positive numbers. So domain is all positives and the range is all real numbers. The next thing is that it's continuous, increasing, and one-to-one. And so what one-to-one means is that for every output value, there is only one input that takes you to that output. So an example of something that's not one-to-one would be a parabola. All right, so a parabola is a nice, easy example of something that's not one-to-one because I can select an output and I have two different input values that lead me there. And the last property of the natural log function is that it is concave down. All right, some log properties. When a and b are positive and n is rational, we have that the natural log of 1 is 0. The natural log of a product is the natural log of the sum of the two things, so natural log of a plus natural log of b. If I have natural log of a to a power, then it's going to be equal to n times the natural log of a. And if I have the natural log of a quotient, a over b, then it's going to be the natural log of a minus the natural log of b. All right, this should all be pretty familiar to you. I don't expect any of this to be new. It might be things you forgot, but I don't expect this to be new. Okay, the number e, let's talk about it. So the number e is the base for the natural log of e. So we get that the natural log of e is equal to 1, and that's how it's defined. So when we look back at our original function of natural log of x, we see that when we plug in e, we want it to equal 1. Therefore, that's how we're going to define e. So e is that value at the top of my integral of 1 over t dt that will give me a value of 1. And remember your original definition of e that you learned back in Algebra 2, maybe pre-calculus? Is right here, your good old friend, the limit as n approaches infinity of 1 plus 1 over n all to the power of n. Now you should be able to recognize this when you see it, okay? So that's kind of my expectation, is that if you notice that in a formula, you should be like, I think I know what that might be. Okay, you might not have it memorized, but you should be able to recognize it and say, I think that's important. All right. Here is a graph of the natural log of x, all right? And so remember that the exponential function e to the n and the natural log of x are going to be inverse functions of each other. Okay, here are some formulas you might want to write down. So the derivative of natural log is 1 over x for x greater than 0. And the derivative of natural log of a function of x, u, is going to be, we're going to use that good old friend, the chain rule. So you get 1 over u times du over dx, or derivative of u over u, where u is positive. Okay, So let's go through a couple examples, and we're going to go through them together. If you're feeling frisky, you can go ahead and pause the video and try these on your own, and then hit play and see how you did, or you can fast forward and just check out the answer. I don't really care how you use this video for that, but I want to make sure that you try all these examples, whether you're following along with me or doing them on your own. Okay, so our first example is to differentiate the function f of x, which is the natural log of x times x squared plus 1 squared, all over the square root of 2x cubed minus 1. Okay, so the first thing I'm going to do is I'm going to break this down using the properties of natural log into a bunch of smaller logs that might be easier to manipulate. Okay, so since I have a product on the numerator, I know that the numerator is going to be the natural log of x plus the natural log of x squared plus 1 squared. And then I subtract from that the denominator inside a natural log. So natural log of the square root of 2x cubed minus 1. And then the next thing I'm going to do is I'm going to take out those exponents and put them in the front. So on my second term, I have a 2 that I'm going to put out front. So now I get 2 natural log of x squared plus 1. And then that square root is really an exponent of a half. So I'm going to pull that out. So I get 1/2 natural log of 2x cubed minus 1. So there's nothing more I can do to separate these. Remember, if I have addition or subtraction inside the logs, I can't do anything. You can only do something if there is exponents that apply to the entire inside, or if there is multiplication or division as your big operation, where the subtraction or addition happens within the multiplication, not outside the multiplication or division. Okay? So that's as far as I can break that down. So now my next step is to go ahead and take the derivative of each of those terms. So the derivative of the first term is 1 over x. And then the derivative of the second term is going to be, well, I have that 2 out front, and then 1 over the inside of the log times, chain rule, times the derivative of the inside, which is 2x. And then my last term, I have 1/2, I have that negative, and then I have 1/2, and then I have 1 over 2x cubed minus 1 times the derivative of the inside of that, which is 3 times 2x squared, or 6x squared. Okay, so now if I simplify, I get 1 over x plus 4x over x squared plus 1 minus, and then a 2 cancels here, so I get a 3x squared on the numerator over a 2x cubed minus 1. Okay, and so that's our final answer. That's our derivative there. All right, let's try the next example. Next example, find the derivative of y equals x minus 2 quantity squared divided by the square root of x squared plus 1. Okay, oh, and for here, this one, we also got to make sure that x cannot equal 2. That should be part of the problem. I forgot to type that on there. I apologize. All right, so this one is, we're going to use a trick. And so because we don't have that all of this is a natural log, so we can't break it down like we did our last one, but we can put a natural log in the problem, which could help us break it down like the last one. Okay, so if I take the natural log of both sides, I get that the natural log of y equals the natural log of x minus 2 quantity squared over the square root of x squared plus 1. And now I can break it down. So I get the natural log of y equals the natural log of the numerator, so x minus 2 quantity squared, but I can pull that exponent out front, so I'm going to do that right away. And then the denominator, so because on the denominator, minus square root means a half exponent. I'm going to pull that out front in that step. And then x squared plus 1 on the inside. Okay, so we got that. So now what I can do is I can go through and let's take the derivative of the right-hand side. So if I take the derivative of the right-hand side, I have a 2, and then 1 over what's inside the natural log, and then the derivative of that is just 1, so I don't need to worry about that, minus 1/2, and then I have 1 over x squared plus 1 times the derivative of the inside, which is 2x. And so now I have to think about taking the derivative of the left-hand side. And so when I take the derivative of the left-hand side, I get 1 over y. But remember that y is a function of x. So I need to use my good old friend, the chain rule, and also multiply by the derivative of y. So that's my chain rule. Okay, since y is a function of x. Okay. So now let's continue. So now I have y prime over y equals 2 over x minus 2 minus, let's see here, oh, some 2's cancel, and I get x over x squared plus 1. Did I do that right? Yes. Okay. So now my goal, remember we're solving for y prime, so we can multiply both sides by y, but all right, here comes some tricky stuff. Sometimes you don't know when to simplify, and sometimes you will know when to simplify in terms of combining like terms and things like that. So I don't really have a suggestion for you. I will always make it clear on an assessment when you need to combine terms or things like that. And if you have questions, you can ask. Otherwise, when you are looking on CalcChat for the answers, sometimes it's obvious what they did, sometimes it's not. So sometimes play around with your answer using algebra to see if you can figure out how they got their answer from what you did. All right, so that'll make sense in a minute. So the next thing we're going to do is we're going to find a common denominator and combine these into one fraction. Okay, so I'm going to multiply the first fraction by x squared plus 1 over x minus 2 minus x times x minus 2 times x squared plus 1. And then I'm going to go through and distribute, and I get 2x squared plus 2 minus x plus 2x. Oh, that should be an x squared plus 2x. And then my denominator, x minus 2, x squared plus 1. You always leave denominators in factored form, okay, unless you're combining fractions. And then from there, I can, let's see here, do I have any like terms? Yes. So my numerator now is x squared plus 2x plus 2, and then x minus 2, x squared plus 1. And remember that equals y prime over y, and we're solving for y prime. So I'm going to multiply both sides by y so that it cancels. And remember, what does y equal? Well, let's zoom all the way back up to the top. Y equaled my original problem, which was x minus 2 quantity squared over the square root. So let's insert some space here. Okay, so now I have that y prime equals this gross fraction, x squared plus 2x plus 2 over x minus 2, x squared plus 1 times y, which was x minus 2 quantity squared over the square root of x squared plus 1. So now if I look, I can see that I have x squared, or x minus 2 here and x minus 2 there. And what else do I have? Oh, I have right here, these two are the same too, x squared plus 1, x squared plus 1. So when I cancel, I get an x squared plus 2x plus 2 on the numerator times only 1 x minus 2. And then on the denominator, that one gets canceled. And then I can combine these. So I have an exponent of 1 and an exponent of a half. So I have x squared plus 1 to the 3 halves. Okay, so since we had a lot of common factors between our, whatever we want to call it, ratio that we multiplied by y, we wanted to make sure we combined those, okay? All right, and so that is it for section 5.1. So now let's talk about integrating. So here are some log rules for integration. So if I integrate 1 over x, we get the natural log of the absolute value of x. And if I integrate 1 over u, I get the natural log of the absolute value of u. There are proofs for these if you want to see why all this stuff works. In your book has all the proofs I don't really want to go over all of them, but if you are really interested, I would be happy to go over it with you during a conferencing period if you really want to know. Okay, so here are some guidelines for integration, and maybe we'll come back to these after we go over the examples. So essentially, it kind of tells you what order to try things in. So the first thing is just kind of look for your basic integration list. And I'm going to put a, didn't mean to do that, sorry. I'm going to put a list of all of the derivative and integration formulas on Schoology so you can have it easy access. You can print it if you want to. Okay, so this will be on Schoology for you. It'll be one page with all of them. So that'll be super helpful. All right, so find a formula that you think is going to work. Try U substitution. If that doesn't work, see if you can alter it. So altering it kind of like we did with the log stuff. Okay, so we altered both of those. One of them we broke our log apart. The other one we took the log of both sides. See if there's a trig identity you could do. And we're going to actually do long division in one of the examples below. And otherwise, like, kind of see what's going on with the function. Maybe you want to graph it and take a look at it and see what the graph looks like or something like that. Okay? All right. We have, I think, 2 more examples. 3. Sorry if that's making you dizzy. I didn't mean to scroll down for everybody. Just wanted to see for myself. Okay, our first example is let's integrate 1 over 4x minus 1 dx. For this one, I see 1 over a function, so I'm going to do good old U substitution. So I'm going to let U equal 4x minus 1. And so then du dx is going to equal 4, which means that dx is going to equal 1 over, or 1/4 du. All right. So I am a little different in terms of how I do U substitution than how I think Catherine taught you. In the way I do it is I do it like this, and then I substitute this in. So now I have that dx equals 1/4 du. So I replace that with the 1/4 du. So now my integral, let me use a different color, is 1 over u, and then the dx is 1/4 du. So now everything is in terms of u. So I have 1/4 times the integral of 1 over u du. So then I get 1/4 times the natural log of the absolute value of u. And don't forget your plus c. And so then I can go back and substitute in my value of u. So my final answer is 1/4 times the natural log of the absolute value of 4x minus 1 plus c. Okay, next problem. Our next problem is a fraction where we have quadratics on both the numerator and the denominator. And a tip for these to make them simpler is to use long division if the degree of the numerator is the same or larger than the degree of the denominator. Okay, so let me write that down. So long division is helpful, sometimes, not always, if the degree of the numerator is greater than or equal to the degree of the denominator. Okay? So let's refresh our memory on long division. So we have x squared plus x plus 1, and we're dividing that by x squared plus 1. And so what I want to do is I want to look and say, okay, what do I multiply x squared by to get to x squared? I multiply it by 1, and then I say, okay, x squared plus 1 times 1 is x squared plus 1, and then I subtract that. So I'm subtracting that, so subtraction, and my remainder is x, and I know it's a remainder because I can't multiply this by anything to get to x. So then I get that my new integral is 1 plus the remainder, x, over the original denominator, x squared plus 1 dx. So I can split that up into 2 integrals, 1 dx plus x over x squared plus 1 dx. I have no idea why my pen started writing thicker. It's very interesting, but that's okay. All right, so now we have this, which is easier because we can go through and we can see that the first integral is really easy, and then the second one is just some basic U substitution. So I get x, and then over here, so if I let U equal u equal x squared plus 1, then du dx is going to equal 2x. So then I get that dx equals 1 over 2x du. My gosh, I am sorry that it is moving around like that. Okay, so then when I plug that all in, I get x over u times 1 over 2x du. If you don't like it this way and you just say, hey, I noticed that the derivative of the denominator is in the numerator and I just need to multiply by a half, then you can do that and pull out your half. I don't care if you do it this way or if you do it the other way. It doesn't matter to me, however you want to do it. But to me, I just make less mistakes if I do it this way. So that's how I always do it, and that's how I show my work. So now I get x plus 1/2 times the integral of 1 over u du, or x plus 1/2 times the natural log of the absolute value of x squared plus 1 plus c. Oh, I actually don't need the absolute value bars because x squared plus 1 is always positive, so I don't need to emphasize that I have absolute value. So there we go, and that's our answer for that one. And our last example is finding the integral of tangent of x dx. So for this one, if I go through all of my things, I know that tangent is sine over cosine, and I know both derivatives and antiderivatives of sine and cosine, so I'm going to use my trig identity. And I'm going to say this is the same thing as the integral of sine x over cosine x dx. And then if I let u equal cosine x, then du dx is going to equal negative sine x. And so then when I plug that all in, I get my good old friend sine x over u times du over negative sine x. The signs will cancel, and I have the negative integral of 1 over u du. So then I'm going to get the negative natural log of u, which is the cosine of x. So the absolute value of that, plus my good old friend c. You can do that with all 6 trig functions to find the integrals for all of those. And so the formulas for those are right here. So we have, of course, the integral of sine is negative cosine. The integral of cosine is sine. Tangent we just found is the negative natural log of the absolute value of cosine. Cotangent is the natural log of the absolute value of sine. Secant is the natural log of the absolute value of secant plus tangent. Cosecant is going to be the negative natural log of the absolute value of cosecant plus cotangent. Okay, so that is all I have for you today. If you have questions, bring them to class, email me, and your homework should be posted. Thank you.